Hello friends, today we are going to discuss about Maxwell's equations. Maxwell's equation. So what are the Maxwell's equations? So these are nothing but the four basics law that we have got in uh, electricity and magnetism, right? But what are the basics laws that we have got? First one, we have got Gauss law of electrostatics. So that is nothing but surface integral of E ds is equal to charge Q enclosed by epsilon naught, right? Then next, Faraday's law. That is integration E dot dr vector is equal to minus del by del t uh, of phi, where phi is nothing but integration b ds and cap, right? Then next one is Ampere's law. Which is modified by Maxwell. Maxwell, right? That is the modified, Ampere's law is original Ampere's law is this one, that integration b dot dl minus mu naught I, right? This is the original Ampere's law that is given by Ampere's. So it is modified by Maxwell in this way, plus epsilon naught partial derivative of surface integral E dot vector ds, right? We have got this. Okay, this is modified by Maxwell. Then also we have Gauss law of magnetic fields, right? Gauss law of magnetostatics, you can say. Right. So these are the four equations. Here this one is given by that should be surface integral ds and cap is equal to 0, right? So these are the four equations of these are the Maxwell's equations, four equations. This is the first, then next one is this, and here is the Ampere's law, and this is the Gauss law of magnetostatics, right? So now Here our topic of discussion is the modification of Ampere's law. So when you are in senior secondary level, so you have already got those derivations of Gauss law, Faraday's law, Ampere's law, and Gauss law of magnetism, or in earlier semester you have already got if you have studied electricity and magnetism, right? Now our topic of discussion is the modification of Maxwell's law. How do we modify how Maxwell modified this Ampere's law? Let us discuss that. So before I explain the modification of Ampere's law done by Maxwell, let me explain why the modification required. Now the Ampere's law uh, was given by line integral bdl b dot dl is equal to mu naught I. This is the integral form. So here I is the steady current. Now you see, if you apply Stokes theorem that you have got in vectors, if you have studied vector, so this line integral can be converted into the surface integral using curl, right? This is ds now, and cap mu naught, and I is nothing but integration z ds. Here z is the current density. This is current density, right? This is current density. Now you see, if you compare the both right hand side and left hand side, here you see this is ds, this is also ds. So we can write curl b is equal to mu naught j, right? So we can write curl b is equal to mu naught j, right? So now you see, taking divergence on both sides, we can write del dot del cross b is equal to mu naught del dot j. That's what we get. Now here you see this term will be equal to 0. This is a vector property, mathematical rule. So divergence of a curl of a vector is 0, right? So this term will be equal to 0. Okay, so that's why we're gonna get mu naught divergence, just wait, of j is equal to 0. Why? Because this term divergence curl of vector b is equal to 0. Okay, so hope you have understood this. So in this case, then we will get del dot j is equal to 0. Okay, so now you see this del dot j, that is nothing but minus partial derivative of rho by del rho, partial derivative of rho with respect to time t, that is equal to 0, right? So here you see, remember this equation, that del dot j is equal to minus del rho by del t. Okay, so now you see, what is the significance of this minus sign? Let me tell you. Suppose you have a volume and enclosing a charge rho, charge density rho. As the current density increases, this that means del dot j here, when del dot z increases, then rho, this charge density decreases. That's why it is negative sign, right? When this flux is outward, flux current is suppose outward direction, then if there is positive charge, when it is outward, then we used to consider del dot z is greater than 0. In that case, this charge density will decrease. So that's why this minus sign comes here. So hope you have understood this, and this is called equation of continuity. Equation of continuity. This is equation of continuity, right? So now you see, so if derivative of rho is 0, right, we know that derivative of constant is equal to 0. Constant is equal to 0, right? So that is why derivative of rho is 0. What does it mean? That means rho is equal to constant, right? Rho is equal to constant. So here from this result we can say that Ampere's law is applicable. Ampere's law is applicable when del dot z is 0 or charge density is constant, right? So that's why Maxwell modified this equation, because that means as the law given by Ampere was applicable in case of steady current only. That means in case of when rho is constant, right? So now if you take the example of a capacitor, right? Suppose if you take the example of a capacitor, so this is a capacitor, suppose, right? So here this is positively charged plate and this is negatively charged. So here we will get a magnetic field and also an electrostatic field, right? Also electrostatic field, and also we will get a magnetic field, and this magnetic field exists due to the change in charge on these plates, and it lasts till the change in charge continues. That means change in rho continues, right? And the existence of the magnetic field between between these plates, there must be an electric field, right? And that electric field comes due to a displacement current. Okay, so there must be another term that is missing in this law. That is what given by Maxwell. So Maxwell's modification of Ampere's law. So now, so what Maxwell's considered. So now here you see, let me write here, Maxwell's modification of Ampere's law. So he considered that curl B is equal to mu naught J. This was the original Ampere's law. So Maxwell considered there must be another term missing here, that is suppose x. Let me consider this one x. So let us obtain the x now. What is x? So before that, again, what we can do, we can take divergence on both sides. Divergence of curl of vector b, right? Then again here also mu naught divergence of vector j plus divergence of x. And again it's a property of vector that divergence of curl of vector, that's gonna be equal to 0. That is why we will get mu naught del dot j plus del dot x is equal to 0, which implies del dot x is equal to, simply you can write del dot x like this as well, is equal to minus mu naught del dot j, right? Del dot j, and del dot j is nothing but, you know, partial derivative of rho, right? From equation of continuity, from this equation we know that del dot j is nothing but minus partial derivative of rho with respect to time t. That is what we have used here. So this is equal to mu naught del rho by del t. Okay, now you see from Gauss law, let me scroll down the page. Okay, from Gauss law we know that divergence, the differential form of Gauss law of E, that is rho by epsilon naught, rho by epsilon naught. Okay, so from here we will get rho. So from where we have got, this is from Gauss law. So rho is equal to this, right? That is what we have got. Now let us use this value of rho here. So then what you will get? Therefore we will get del dot x is equal to mu naught epsilon naught del t of del dot e, right? Del dot e. So we can interchange the operator here. So del dot mu naught epsilon naught del e by del t. That is what we can write. Okay, so now you can see, let me scroll down the page. If you compare the both left hand side and right hand side, right, then you will get x is equal to mu naught epsilon naught del e by del t. So this is the value of x, right? This is the value of x. Now you see, let me take this equation, let me go upward. Let me take this equation as equation number 1, right? So, and this is equation number 2, right? So now here you see, just wait. Now use this equation number 2 in this equation, in the above equation. Here you can see in this equation, in equation number 1. So this is the equation number 1, right? So here we're going to put the value of x. And what is the value of x? This is the value of x. So equation number 1 was that curl of vector b is equal to mu naught j plus mu naught j plus x. So here we're going to put the value of x from equation number 2. So this was equation number 1, right? So using 2 in 1, what we're gonna get? We're gonna get curl B is equal to mu naught J plus mu naught epsilon naught partial derivative of vector E with respect to time t. So here you can take mu naught common, then the equation becomes mu naught J plus epsilon naught del E by del T, right? Del E by del T. So here you see this is the modified Ampere's law. This is the Ampere's law modified by Maxwell, right? So this is the modified Ampere's law, right? And from this modification, the concept of displacement comes. So here you see this term in this case. So this term J vector plus partial derivative epsilon of partial derivative of E with respect to time t. This is displacement current density. This is called displacement current density. So, and displacement current, so we used to write this one by ZD. You can let me write here ZD to represent displacement current density, and displacement current ID, that is equal to integration ZD ds, right? So this is displacement current, right? So hope you have understood. In the next lecture we're going to discuss how to convert integral form to differential form of those Maxwell equations, right? And differential form to integral form. Okay, so stay connected, and if you are new to my channel, please subscribe the channel, and if you think these videos are helpful, then please share with your friends and hit the thumbs up button, and also hit the bell icon so that you get notified when new video will be uploaded. So thank you for watching. See you in the next video.